Um, so we're going to talk today about acoustic phonetics. So last time we talked about articulatory phonetics. That's used a lot when we want to, I need to make sure I'm recording through the right microphone here. And all of my chattiness, I forgot an essential step. Can you hear me, Jeremiah?
Yes, I can hear you.
Convenient purpose. Okay. All right. We're going to talk about, as soon as I start recording. Oh, we are recording. We're going to talk about acoustic phonetics. So articulatory phonetics is about what is going on in your vocal tract when you make speech sounds and how you can characterize speech sounds based on those articulations. Acoustic phonetics is about the sound signal that those articulations produce. So it's about the sound waves that come out of your vocal tract and that are heard then by listeners. So it's about these things. Now, just to foreshadow a little bit, when you look at this artist's rendition of a sound wave coming out of somebody's mouth, you don't just see one little wave, right? You see a whole bunch of waves superimposed on each other. And this is a key concept that we'll return to as we're talking about acoustic phonetics. The fact that we don't produce simple sine waves when we're talking, we produce a bunch of sine waves superimposed on each other, what is called a complex wave. And much of what we'll talk about is based on the idea of complex waves and what we can do to manipulate, analyze, and understand the complex waves that are produced during speech. Here are our objectives. So by the end of this lecture, you will have learned, we hope, the basic elements of speech acoustics and the digital processing of speech. So you'll learn about complex waves and waveforms, Fourier analysis and spectra, spectrograms, which are a visualization of spectra over time. So you'll learn that. You'll also learn about the tube resonator model of speech acoustics that allows you to relate articulation with acoustic signals. You'll learn about the relationship between harmonics, resonances, and formants. And this is something that is hard for most students. So this is not easy to get your head around or to keep these straight. So we'll spend a little extra time clarifying that. You'll learn how to predict the frequencies of resonances from the length of vocal tracts and how changes in the shape of the vocal tract affect the frequencies of resonances. That is perturbation theory. That ties back to this. So the tube resonator model of speech acoustics is the basis for perturbation theory. So we're going to start with kind of a high-level introduction to ways that we can represent speech acoustics. A lot of this will be familiar to you if you've done a lot of physics, where you've talked about physical systems that involve oscillation or waves or anything like that. Who here has taken a physics class? Who here has taken 2 physics classes? Who here has taken 3 physics classes? So some of you have a certain amount of physics. That's going to be helpful as we're talking about this. And so we'll rely on you to provide some insight into some of the concepts that we talk about. So the first thing that we're going to talk about as a representation of speech is a waveform. And what waveforms show is sound pressure over time. So you have sound pressure on the y-axis and time on the x-axis. So that's one very important way of representing speech. And that's probably the one that's most familiar to most people, right? I assume most of you have probably seen like a waveform before. Is that safe to say? Yeah, so waveforms are one representation, and they're useful for understanding some aspects of speech acoustics. Other representation is a spectra. So spectra show sound pressure over frequency. So if you look at this chart here, then on the y-axis here, you have sound pressure. And on the x-axis, you have frequency. And this is basically looking at one slice of time, one little slice of time. And it's saying that at that slice of time, the complex wave that was encoded in that waveform we saw earlier has a sound pressure of about, let's say, 10 at this frequency. So there's a wave in that complex wave that has the amplitude or pressure of about 10, about this much, at this frequency. So that might be a little bit confusing at this stage, and we'll come back to it. But this is an important kind of visualization and an important kind of representation for acoustic phonetics. And in fact, this is something that is used quite a bit in speech technologies too. So different kinds of speech technologies will take sequences of spectra as an input, or some representation of the spectrum as input. And we'll talk more about that later. The spectrograms show sound pressure over time and frequency. So spectrograms are basically a bunch of spectra that you've arranged one after another over time. And the higher those peaks are on the spectra, the darker the shading is on the spectrogram. And they're very useful in doing acoustic phonetics because they're one of the most important visualizations for acoustics, because you can see all sorts of things in a spectrogram that you wouldn't be able to detect otherwise. And in fact, a really good phonetician can look at a spectrogram and they can read it back to you, because all of the information that you need to reconstruct the acoustic signal is basically there in the spectrogram. So let's get down to nitty-gritty and talk more about some details, and hopefully give you a better understanding of what these representations, waveforms, spectra, and spectrograms are all about. And in particular, how you get from waveforms to spectra and spectrograms. That is Fourier analysis. So complex waves, and this is all waves that originate from the human vocal tract. They're all complex waves. They are waves consisting of more than one component. And by component, we mean basically a sine wave. You know, the simplest kind of wave, a sine. So basically, you get a complex wave by adding a whole bunch of sine waves at different frequencies and changing frequencies over time together, and you get a complex wave. And likewise, if you have a complex wave and you want to get a spectrum from the complex wave, or look at this complex wave over time and get a spectrogram, then we're going to break that complex wave up. We're going to factor it down to individual sine waves with different amplitudes at different times. And that's basically what a spectrum is. So here we have a complex wave, and it consists of sine waves at different frequencies and different amplitudes. So what Fourier analysis or Fourier analysis does is it decomposes complex waves into a series of sine waves. And this is one of the fundamental types of processes, of procedures in the analysis of acoustics, and a particular kind of Fourier analysis called fast Fourier analysis, or the fast Fourier transform, is used extensively in digital signal processing. So basically, it takes a wave, like here we have a sawtooth wave. So it's like this, 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 this. And you might think, oh, that's just a wave. But actually, that sawtooth wave consists of a whole bunch of simpler waves, a whole bunch of. And Fourier analysis takes this and converts it to this. You can characterize at any point in time a complex wave as a sequence of numbers, of pairs of numbers, where one number is the frequency of a sine wave and the other number is its amplitude. So this is we're not going to do the math for Fourier analysis, but it's very important that you understand the concept. So who can repeat back to me the idea of Fourier analysis? Anyone want to give a shot at this? Hopefully I wasn't so incredibly unclear that you're incapable of doing this. Yes?
Well, just to decompose a complex wave into its component sine wave.
Yeah, exactly. Fourier analysis, including the fast Fourier transform, allow us to decompose a complex wave into a sequence of sine waves. When we do that, when we decompose a complex wave into a sequence of sine waves, and we look at those sine waves at one slice of time, then we get a spectrum. So spectra are visualizations of analyzed waves at single slices of time. You're taking these sinusoidal components that you got via Fourier analysis, and then you're plotting the average amplitudes, basically, not exactly right, but you can put it that way, of each of the component waves according to their frequencies. So each of these little peaks that you see there, not the big peaks like this, but the little peaks, each of the little lines you see sticking up there represents a sine wave with a particular amplitude. And spectra are very useful because they show the distribution of energy within a complex wave at a particular point in time. So you can see that there's a concentration here and here and here, and these we will learn to call formants. These are groups of these little peaks, which we will learn are called harmonics, that are relatively prominent. So, so you can see formants on a spectrum. Who here has made spectra before? I know some of you have taken linguistics classes in the philosophy department. Christina could tell you all about this stuff, even more than we could. But you can see formants, these prominent group of peaks or harmonics using a spectrum. But you can see them even better in some cases on a spectrogram, and you can see, oh, so much more. So in a spectrogram, you have basically spectra over time. So this axis, the y-axis, is frequency. So we sort of turn the spectra on their sides. So this is frequency. This axis is time. So you read it from left to right, traveling through time. And this z-axis that's represented by darkness represents amplitude or sound pressure. And it's this incredibly useful visualization that linguists use all the time, but other people use them all the time too. So people doing speech technologies now that computers are more powerful, will often feed mathematical representations of spectrograms directly into speech models that do speech synthesis and speech recognition. So these are really useful. This is a really useful concept, a really useful way of understanding the acoustics of speech. So just to quiz you a little bit, what does it mean if we see a dark band here? What can you infer about the acoustics of this utterance? What can we say about this sound wave?
There's a high amplitude at that frequency.
Okay, so at this time range, at this frequency, there's a relatively high amplitude. And in fact, there is, it's probably a kind of a bunch of sine waves, a bunch of simple waves that are next to each other that are relatively high in amplitude in that region. So that looks like what we call formant, which we talked about back here when we were looking at a spectrum. Any questions so far? I promise it gets even more exciting. So now we're going to talk about something that's very confusing for a lot of people, and that is the distinction between resonances and formants. So far we've talked about formants, and I used the word harmonics. Who here has heard the word resonances before? Can anybody define a resonance?
Like a resonant frequency?
Like a resonant frequency. Yeah.
It's a frequency where waves in some sort of enclosed environment reinforce each other and become louder. Certain cavities have like specific frequencies that are aligned such that waves constructively interfere instead of destructively interfere.
Yeah. So a lot of physical systems are like this, as we'll see. They tend to favor energy particular frequencies. And so waves at those frequencies will sort of be reinforced, like was said. Whereas other waves at other frequencies will tend to be dampened. And those frequencies where waves are getting reinforced are called resonances. Here are some definitions. So a harmonic is one of the sinusoidal components of a complex wave. In speech, these are at whole number ratios to the fundamental frequency. Well, what is the fundamental frequency? Well, it's the lowest harmonic. So the fundamental frequency, also called F0 or H1. By the way, why is the same thing called F0 and H1? Can they get their indices straight? Well, this is linguists at their best. They love, this is one thing that you'll see in this class. Linguists love confusing terminology. And so this is your first big example of this. The F0 and H1 are the same thing. They couldn't call it H0, they had to call it H1. So this is the lowest component or harmonic in a complex wave. So in voiced speech, in speech where your vocal folds are vibrating, like typically vowels and voiced consonants, then this is the rate at which the vocal folds are opening and closing. And a resonance or resonant frequency is basically what we've already said. So it's a frequency that if energy is added to a physical system at that frequency, there'll be a relatively large response. So what happens is if you're a harmonic and you're lucky enough to be near a resonant frequency in your frequency, then you get sort of amplified. But if you're not one of the lucky duckies and you're between resonant frequencies, then you get dampened. So basically, physical systems are not very egalitarian, and some harmonics are just born to wealth by being next to a resonant frequency in terms of their frequency, and other harmonics are not so lucky. So harmonic, fundamental frequency, resonance, and then formant. So a formant is a band of relatively high amplitude harmonics. And the reason that they're relatively high in amplitude is they were next to a resonant frequency. They were right around a resonant frequency. So you can, in fact, see where the resonant frequencies are if you put a complex wave through them, that such as the sort that would come directly from your vocal folds, from your glottis, through the system. Then the harmonics where there are resonances are going to be relatively prominent. That is, they're going to form formants, whereas the others are going to be dampened. So I'm going to quiz you a little bit. I'm going to give you a definition in different words, and you're going to tell me what the term is. Okay. So what if I say that this thing is a cluster of harmonics that are near a frequency at which a physical system has a relatively responds relatively well, or provides a relatively large response. So what term am I referring to? Yes. A formant, right? A formant. So what if I say that this is one of the simple waves that makes up a complex wave, and it's at a whole number ratio to its the lowest frequency component within a complex wave? What am I? Yes. A harmonic, right? And what if I say I am that lowest frequency component in a complex wave? Yes. H1. H0. No. Finally, let's say I'm a swing set. No, better yet, I'm a swing. And no matter how fast or how slow you push me, I only go one speed. In fact, I only really respond to you pushing me at that one frequency. What is that frequency? Yes. It's the resonant frequency. And like for a pendulum, you just have one resonant frequency. But for other kinds of physical systems, like the vocal tract, you have basically an infinite number of resonant frequencies. So here are formants. Formants are high energy regions in the spectrum. So we call them F1, F2, F3, and so on. But it's really F1, F2, and F3 that are most important to speech acoustics. Some of the higher formants actually are sometimes important for certain sounds, but for the most part, it's these three that are important. And in fact, any vowel in the world, in any language, can be characterized by the height of F1, F2, and F3, by the frequency of F1, F2, and F3. Or if they're what are called diphthongs, which is vowels where your mouth is moving at the same time, they can be defined by the kind of curve of the formants. So for homework, for this unit, for this module, then you'll actually take and record words in your native language, whatever language you feel you speak best. So you're going to take and record words that have all of the different vowel sounds in that language. And then you're going to extract the formants. You're going to make spectrograms and extract the formants for each of those vowels. And you're going to do a vowel plot, a nice plot of those vowels, showing where the different vowel sounds in your language are in this space. We're going to concentrate specifically on on F2 and F3. Or sorry, F1 and F2. So you'll do F1, F2 plots for all of those vowels. And we will expect you to know how to measure them by hand, because that's helpful to understand what is going on in a spectrogram. But mostly we'll have you use a script in this program called Prat to extract the formant values. And then you can plot them however you wish, as long as it's exactly how we say it. So any questions about this? Formants are very important. Formants are actually important to consonants too, but they're especially important to vowels. Yes?
You said there's like an infinite number of resonant frequencies for a vocal track.
Yeah.
How does that work?
Well, we'll see the formula in a minute, like the equation that allows you to calculate the resonant frequencies of a vocal tract. So it's just an infinite series, and that means that potentially there are an infinite number of formants, but the sound energy, the waves in speech and in a speech signal tend to be concentrated somewhat. The energy is somewhat low, so it's hard to actually detect some of these higher formants as you go on up, because the envelope is sort of biased towards the fundamental to some degree. The fundamental being the fundamental frequency. That's another term for this thing. That linguists love this. So it's fundamental frequency, F0, H1. It's like they just do obscure the truth.
Computer scientists do. Deep learning, that's.
Yeah. Well, I can make fun of linguists because I'm a linguist. I'm not really a computer scientist, although I obviously teach in a computer science department. So I like to make fun of linguists. But yeah, computer scientists also have confusing terminology and sometimes very inexact terminology, like multi-layer perceptron. So it's not actually a perceptron, but you call it a multi-layer perceptron. Anyway. So we're not the only guilty ones. So frequency, wavelength, and velocity, the velocity at which a wave travels, or which sound travels in this case, are mathematically related. And this is the very nice formula. Adobe trying to me something. So this is the nice formula here. So if you know frequency, F, and you know velocity, C, then you can predict wavelength. And likewise, I mean, if you know any two, then you know the other one based on this frequency, this formula. And the basic thing that it shows you is that frequency and wavelength are inversely related, right? It's kind of intuitive, but it's nice to have a formula. Were you raising your hand or are you stretching? Stretching too. So tubes have resonances, and you know, my vocal is a very special vocal tract. It's different from any vocal tract. It has all sorts of bumps, curves, and everything like that. But when a phonetician looks at you, looks at your vocal tract, they just a tube that is closed at one end. The end at which it's closed is where your glottis is, your larynx, and in which it's open is your lips, assuming that you have your lips open at the time. And a closed tube like that, a tube closed inside, has an infinite number of resonances. And this is what the first three of them look like. Cute. So for R1, then a complete wave, a complete cycle goes clear out here. Oops. Oh, I hate it when it does that. Apple, I hate you. So this basically, the wave is extending out here and beyond. So that's R1, the first resonance. Here we have R2, the second resonance, and here we have R3, the third resonance. And I'm going to tell you a secret. R1 is responsible for F1. R2 is responsible for F2, and R3 is responsible for F3. So this time it's not confusing because it lines up exactly. The first resonance gives you the first formant, and so on ad infinitum. And you can predict the frequency of these resonances because you know the wavelength, because you know how long the vocal tract is, because you can measure it.
Does anyone know how long your vocal tract is?
You don't know how long you'll never become phoneticians. No. So I don't remember how long my vocal tract is. When I was in graduate school, and we had a phonetics class from a famous acoustic phonetician, and he one of the exercises that he did, or one of the demonstrations, was calculating the length of somebody's vocal tract, in real time. Like we would bring them up on in front of the class and record them and compute the formants and say, okay, your vocal tract is 19 centimeters long, or whatever. But I'm not going to do that.
But it's something like 15 to 20 centimeters?
I think it's roughly in that range, yeah.
And it goes from here.
It goes from here, from right about here, up to your lips.
But kind of curved.
Yeah, it curves, but acoustic phoneticians don't really care about that curve. It's like noise, So we'll factor that out because it would make the model more complicated. So if you pretend there's no curve, then you can calculate the sequence of resonant frequencies this way, with this formula. So F is frequency, N is an odd integer, C is the speed of sound, velocity, and L is the length of the tube. So this is a very simple formula, but it's kind of an approximation. It's not actually the exact, it will not give you the exact resonant frequencies because the diameter of the tube also plays a small role in determining the resonant frequencies. So to compute things more accurately, you have to use this formula right here. which is not much more complicated. It just has an extra variable diameter, which is d. So this is great. You can calculate all of the resonant frequencies. And without using any hard math. So it's beautiful. Any questions about this? You know, so because n is part of an infinite series, you know, then the resonances are also part of an infinite series. Yeah.
How do we figure out the even resonances if this formula only works for odd integers?
So n is not the number that is by the r, right? So if you so you have another series. So if n is 1, then you get r1. If n is 3, you get r2. If n is 5, you get r3. Does that make sense?
Yeah.
Okay.
Thanks. And then evens are if it's like closed on both sides.
It's a little more complicated than that, but you get when they're closed on both sides, you have a different formula and a different series. So far we've learned some physics, some acoustics, and we haven't really tied these back much to language. These are things that would be true of any physical system, you know, of any acoustic signal. But now we're going to tie this to something specifically linguistic, and that is vowel acoustics. First, we need some more definitions. So a standing wave is a wave that oscillates in time, but whose peak amplitude profile does not move in space. And what we're going to propose is that the waves that are produced and that are bouncing around in your vocal tract are actually standing waves. It's like in water. If you have a little tub and you stick your finger in and it starts like the waves start, then they're just going up and down. The waves aren't really going anywhere. The water is just oscillating up and down, right? So that's a standing wave. And that's what we're saying is really happening, that is important in your vocal tract. A velocity node, getting, you know, further developing the idea of a standing wave, it's a point in the standing wave where the velocity of the particles is least, you know, where they're moving up and down or back and forth the least. For example, at the closed end of it, right? Because they can't move, they're like jammed up against the closed end. So their velocity is very low. A velocity antinode is sort of the opposite of that. Not only is it sort of the opposite of that, it is exactly the opposite of that. So it's where the standing wave, where the velocity of the particles is greatest. So for example, for the first resonance, for a wave at that frequency, then your lips, you know, this is going to be velocity antinode, because the particles are free to move. There's nothing to stop them. So if we go back here, where on this one for R2, where are the velocity nodes. How many velocity nodes are there? Well, you don't have the knowledge you would need to answer that yet. But you know from what I've told you that there's one here. And basically what these lines tell you is how much the particles are moving back and forth. So where else is there velocity node in for R2? Where else does it look like the particles are not moving very much? Yeah. Yeah, right here. So that's a node. And then we have two nodes, one right here and one right here. Well, these are going to be important. Because when we line these up with anatomical landmarks, this allows us to make predictions regarding formants. Yes?
Is standing wave the same as a transverse wave?
No, standing wave is not the same as a transverse wave. I think something can be a standing wave and a transverse wave, but they're not the same thing.
In the water example, it was transverse wave.
Right, right. Yeah, so that would be a transverse wave, right? But it would also be a standing wave, but it doesn't follow that any standing wave is a transverse wave. Because so in the vocal tract, it's not a transverse wave because the wave is things, the sound particles are going smushing and going farther apart, smushing and going farther apart. So, it's not, it's possible to be both, but they're not equivalent. So here is a secret. When you have a constriction at a node, it raises the corresponding resonance. So if I have a constriction at a node for F3, it's going to make F3 higher in frequency than it otherwise would be. And if I have a constriction at an antinode, let me draw this. So if I have a constriction right here around the uvula, if I have a constriction right there, then it's going to raise F3. That's this light gray resonance. If I have a constriction near an antinode, like roughly the same place between the pharynx and the uvula, then I actually lower the corresponding resonance. Okay. And if you do expansions instead of constrictions, then it's just reversed. So this is very clever because it allows us, given articulation, to predict something about acoustics. And this idea is called perturbation theory. So you should write that down. I'm not sure if it's in my slides or not. So there's a general thing that's called perturbation theory in physics, actually, a way of calculating values that you couldn't calculate directly by calculating an easy value and then computing a perturbation, or from that value. And this is an instance of perturbation theory applied to speech acoustics. So there are some very simple generalizations that follow from what we just talked about, from perturbation theory and from the effect of constrictions and expansions near nodes and antinodes upon the frequencies of resonances, and therefore the frequencies of formants. So because of all of this, then the first formant, F1, is inversely correlated with vowel height. Because if you open the vocal tract kind of in the near a node, actually I have to look back here. So with F, to explain this, when you open your mouth up, you're creating expansions near nodes and antinodes. And well, the first formant also goes up. And this is because you have an expansion near a node. And it's basically oops, why do I keep doing that? It's this node. So you're expanding the vocal tract, and so you have an expansion near a node. The second formant is inversely correlated with vowel backness. So this is, again, has to do with moving your tongue around relative to nodes and antinodes. So conventionally, when we plot vowels, as you will do when you plot your vowels, you do it so that the high vowels are at the top, low vowels are at the bottom. That makes sense. High, low. Front vowels are at the left, and back vowels are at the right. Yes.
So I think you said earlier that the formants are harmonics of a fundamental frequency.
So the formants are clusters of harmonics, right? They're not single harmonics. They're always bands of harmonics that are.
So you're doing the shifting harmonics slightly from where they would lie without these.
No. So the harmonics themselves don't move. What moves is the resonances.
Okay.
And so the resonances, by moving, they change what harmonics they favor.
So there's not one fundamental frequency. Right.
So there's one fundamental frequency, and then there are multiples of that fundamental frequency, and those are harmonics. And there are all of these harmonics, and then there are all of these resonances. But you can't see the resonances directly because they are not an abstract property of the physical system. But what happens is if you send all of this complex wave with all of these harmonics through the system, then you see that some bands of harmonics get favored and others get oppressed. And the favored harmonics are formants. And you can see differences in how the vocal tract is configured based on where these formants are. Because that changes the harmonics when you have constrictions or expansions. changes the resonances, excuse me, changes the resonances, and that affects the amplitude of the harmonics, or which harmonics are high in amplitude and which are low in amplitude. So any other questions about this? It's actually incredibly confusing. So if you feel confused right now, don't worry. You're not alone. Other people are confused as well. So if you have any questions about this, now is a good time to ask. Otherwise, I'm going to ask you some questions. Yeah.
Could you please repeat like the change in the resonance that occurs to like constrictions that nodes or
Yeah. So do I have a slide on this? Why don't I have a slide on that? Yeah, so here, I'll write it down here. So let's say constriction and expansion node. No. Okay, so if you have a constriction node, the resonance goes down. If you have a constriction at the antinode, the resonance goes up. If you have an expansion at a node, wait. Sorry, I just told you exactly the wrong thing. I just realized. Okay. Forget what I said before. I was faster than I was thinking. So if you have a constriction at a node, the resonance goes up. If you have a constriction at an antinode, the resonance goes down. So the frequency. So resonances don't have amplitude. Resonant frequencies. So the resonant frequency goes down. The resonance goes down in frequency. So if you have an expansion at a node, then the resonant frequency goes down. If you have an expansion at an antinode, the resonant frequency goes up. And this is that's the right thing. I don't know what I was saying before. So does that clarify? So everybody should write this down actually, because this may well show up on the exam. Like one thing that I've done in the past is given people this diagram and spectrograms and ask them to explain what is in the spectrograms based on this diagram. The difference between two spectrograms. So if you this, and you can read this, then these are actually easy problems, but you should be sure that you understand it. So to help make sure you understand that, I'm going to ask you some questions. Actually, so what happens to a harmonic if it would be near a resonant frequency for a frequency for R1, right? So it would be near R1, except that there is a constriction near an antinode for R1. What happens to that harmonic? What might happen to that? So actually, that was not well formed. So I am a harmonic near R1. Then the nasty speaker makes a constriction near an antinode for R1. What likely happens to me? Yes.
Your computer's gonna shut off. You don't plug it in.
Oh, that's not good. Does anybody have the time? Thank you so much. Thank you. You're a lifesaver. I thought I should bring it, but then I thought, oh, I just had the battery replaced. Everything will be fine. Okay, so what happens to this harmonic near R1? Suddenly, something changes.
Will we draw it on the board while you do that?
Yeah, I'm not sure why
As
this
soon as I
happened.
start drawing it on the board, the internet will come back.
So it's not the internet. It's Apple. Symphony 10.
We have to find chalk.
Okay.
So this is R1. And then you have your vocal cords back here.
Your vocal cords right here.
Oh, okay. Vocal cords, and they have an F0.
They're producing F0,
They're
but
producing F0.
so actually, this is back. So let's.
Okay.
So let's say. Oops. There's a constriction right here at the lips. So I'm chilling, enjoying life near the first resonance. Suddenly, the human makes a constriction at their lips. What happens to me? Yes. Yeah, so the resonant frequency goes down. So if I was above the resonant frequency, I might get even higher. But if I'm, sorry, this goes down. So if I was below the resonancy, I might get even higher. But if I was above the resonant frequency, then I will get lower because I will, the system will not respond to me as much. So what happens to a formant? What is going to happen to the formant called F1 when I make a constriction at my lips? I make a constriction at my lips. This is a constriction at an antinode. At an antinode. So if constrictions at antinodes, as we see right here, or sorry, right here. Happens. Yes. It goes down. And if the resonance goes down, then what happens to the formant? You know, the cluster of favored harmonics. Yes.
The formant goes down.
Yeah, the formant goes down as well. So it's different harmonics that are getting favored, or different harmonics that are getting favored by the resonance because it's shifted. So the formant goes down because the formant is just those lucky ducky harmonics that are getting amplified by the resonance. So what if I'm a harmonic and I'm near a resonance for F3? So that's the light green thing here. And the speaker moves on up towards the alveolar ridge and makes a constriction right here. Let's say I'm above the harmonic. I'm not above the resonance. I'm not close, but I'm in the neighborhood. And there is a constriction at the alveolar ridge. What is likely to happen to me? Yes. Yeah, yeah. So the formant, so that means the resonance shifts up. So the harmonics that are higher, a little bit higher, end up being favored. So in effect, the formant shifts upward. So what this means, if you're looking at a spectrogram and you see a pattern with formants where F3 goes up and F1 goes down, and F2, here's F2 right here. F2 goes up just a smidge. So F3 goes up a lot, F2 goes up a little, and F1 goes down. You see a vowel, and then a consonant and a vowel, and before that consonant, these changes are happening. F3 going up, F2 going a little, F1 going down. What kind of sound is this likely to be? What is the place of articulation of that sound likely to be? I need to find a place that's near a node for F3, a node for F2, and an antinode for F1. And you don't have to be super close to be near. It's just nearer to the node than the antinode, or to the antinode than the node. Yes. Yeah, the alveolar ridge. It's probably at the alveolar ridge. So you can reason from this kind of diagram to things like vowel and consonant, place of articulation. So you want to do another example exercise? Want to do another one? Okay. Let's say I look at a spectrogram. Looking at a spectrogram and going along, minding my own business, and I suddenly see F2 shooting up and F3 dropping. And then there's a consonant. And then F3 goes back up and F2 drops down. What have I observed? What is the place of articulation of that consonant? Could you say that again? Yeah. So here. So you're looking at a spectrogram and looking at the formants. And you see a pattern like this, where this, you know, is some kind of consonant, and this is a vowel, and this is a vowel. And this is F3, this is F2, this is F1. So what happened to produce this formant transition, this change in formants? Where was that consonant produced? Yes. I can't quite hear you, but could you speak up? Yeah, at the velum, right? In fact, this has a name. It's called velar pinch. I like to call it velar death pinch because it sounds sort of sci-fi, Trekkie, whatever. Yeah, you have a constriction here at the velum, and it's near, not really near a node or a node for F. It's near a node for F2, this node right here, and it's near an antinode for F3. And so it has this effect of driving up F2 and driving down F3 so that the two formants get pretty near one another. Good work. So let's move on, and then we can come back to this. Does anybody know how to get rid of that? So we can take our formants and we can make a plot. And that's what you're going to do, each and every one of you. It's going to be a vowel plot. It's not too soon to start thinking about this. And one of the harder questions for a lot of people, at this stage, is to answer what is native language, or what speak the best. I know what language I speak the best, but a lot of other people are very multilingual and may not be able to hide very easily. And if you think it's kind of a wash, just pick the one that isn't English. No, I mean, pick the one that you feel most comfortable with. Who here speaks a language other than English? Who here feels that they speak that language better than English? We got a substantial number of people who will want to do the vowel plot for a different language. So here's a vowel plot for Welsh. As you can see, we have F2 up here at the top. on the x-axis and F1 on the y-axis, and it's the origin is sort of up here. That's how we like to plot them. So it's sort of annoying because you have to make whatever software you're using to do the plotting do some acrobatics, but it's definitely doable, and it makes it more intelligible to other people. So you're going to make a plot like this, among other things, for the language you speak best. So here are the steps that you'll follow. First, you will determine how many vowels your language has. Not easy. Some people think, oh, I'll just look at the writing system, right? You know, figure out how many vowels there are based on that. But this is not always reliable. Obviously, if you speak Chinese, it's not reliable at all because you don't write the vowels separate from the consonants. But if if you spoke English, you might think, oh, English has 5 vowels, E, I, O, U. But actually, in terms of vowel sounds, English has lots of vowels. So in my dialect of English, we have beat, bit, bait, bet, bat, boot, book, boat, bought, and but and but. So I lost count. And a lot of speakers of American English also distinguish between bot and bought. Like Lori makes this distinction. So, by the way, how many people here make a distinction between bought and bought? Are these different words for you? So one. So this is not uncommon in various parts of the U.S. In the UK, then everybody for the most part this distinction, and they make other distinctions that are not in the American English, but don't make distinctions that are made in American English. So it's all very complicated. And figuring out how many vowels your language has is not simple. So you have to do some exploration, maybe look at some descriptive grammars of your language. Start with the Wikipedia page, which often the bibliography will have references for grammars or other works that could help you to.
I actually think that Catherine Young, who's formerly took linguistics and stuff here and now is in her languages here. I actually think she's been going to Wikipedia pages and adding vowel and consonant inventory as a hobby.
As a hobby. As a treat. Yeah. So what you need to do is figure out how many vowels there are, and then figure out words for each of these vowels. Record at least 10 tokens of each of these words. Annotate the recordings using PROT. Using a PROT script, we will provide you extract format matrix from each of these annotated recordings. And then using a visualization tool of your choice, plot the vowels, following the standard conventions. So it should look kind of like this. Anyway.
I think we're probably going to go over this in more detail, but for the carrier words, like you carefully did a B at the beginning and a T at the end of all of them.
Yeah, that's not always possible. That's ideal to have all of the vowels in the same environment, so the same thing before and the same thing after. But that just doesn't work in languages, particularly languages that have sort of long words. So if you're to try to do this with Tamil, then this would be really annoying. Because the words are long, morphemes are long, it's hard to find minimal pairs that differ in just one vowel. So that's good if you could do it, but you don't have to do that. Okay, thank you very much. We're